Hey everyone, welcome back to Real Analysis 1. This will be lecture 4 of the course. In this section we're going to start our examination of limit processes, and we're going to begin with the idea of a convergent sequence. So let's go ahead and jump into it. So we'll call this section 2.1 Convergent Sequences. Okay, so yeah, you can think of this as really our first serious introduction to limit processes, and this introduction is going to involve identifying, being able to prove, and reason about the limit of sequences of real numbers. Okay, and so before we can, just like every lecture, before we can get into the meat of the discussion, we have to lay out a few definitions and some of the key concepts that will be used as part of our constructions. And so the first thing we'll define here is something that I'm sure everybody knows, but we just have to level set on the definition of the absolute value of a number. And so we say for real numbers, x and r, the absolute value of x is defined as, well, we say that the absolute value of x is equal to x if x is greater than or equal to 0, and negative x if x is less than 0. Okay, and so nothing too mind-blowing there. We've certainly seen that. Let's talk a little bit about some of the properties of absolute values that'll come up here. Now, many of these things will be things you've seen, things that you'll have used over, your career in mathematics, and they're just things that we want to restate here as a matter of fact. And we're not going to prove any of these. We're just going to state that many of them are obvious. So the absolute value of negative x is equal to the absolute value of x, and this is of course true for all x and r. Right? That's obvious. That's kind of implicit in the definition. The absolute value of the product of two real numbers is equal to the product of the absolute values of the real numbers for all x, y, and r. Okay, we've seen that, of course. Here's one that we'll be most likely aware of. The absolute value of a number x is equal to the square root of x squared. Okay. And again, for all x and r, I'll stop writing that though. Fourth item here, if r is greater than 0, then the absolute value of x being less than r is true if and only if x is between r and negative r. Right, and so we'll have seen this before, this relationship. I think when you were probably in algebra, maybe college algebra or something like that, you would have been asked to solve inequalities and to think about inequalities that specifically involved absolute values. Okay, and then the last one I'll mention here at the onset is this idea. The negative absolute value of x will always be less than or equal to the absolute value of x, will always be less than or equal to x, which will be less than or equal to the absolute value of x. Right, so x is always going to be between its absolute value and the negative of its absolute value. And that's kind of obvious, I think, right? So those are the 5 properties I think we'll use in the near term when we're dealing with convergent sequences and some of the limit theorems. So I want to start with that one. Then the one that's not on here is one that's very important, which we'll use a lot, and we'll actually prove this one, and that's the famous triangle inequality. Okay, so this is the triangle inequality. And we'll have seen this before, probably if you were in linear algebra, you've seen this before, but basically what the triangle inequality says is that for all x and y and r, all real numbers x, y, the absolute value of x plus y is going to be less than or equal to the absolute value of x plus the absolute value of y. Okay, and so let's prove this one. It's very easy to prove. Okay, so let's just let x and y be real numbers. We'll let x and y be real numbers. Then it's certainly true that 0 is less than or equal to x plus y squared. Okay, so if they're both 0, then of course they are equal to 0, but if either of them are off 0, then when I add them together and square it, I get something larger than 0. And this, of course, is just FOIL this out, you get x squared plus 2xy plus y squared. Okay. And this, according to the previous theorem, is going to be less than or equal to, it's going to be less than or equal to the absolute value of x squared plus 2 times the absolute value of x times the absolute value of y plus the absolute value of y squared. Okay, and then this, if you look at it, we can kind of package this up, and this is really going to be the absolute value of x plus the absolute value of y quantity squared. Okay. Okay. And so recall, in the previous theorem, we said that the absolute value of x is equal to the square root of x squared, right? And we're going to use that fact here. So here we can say that I'm going to flip page. Well, look at this. So we need to see this. So here I'll say that you've got x plus y, the absolute value. Well, we know that this is equal to x plus y quantity squared, absolute value, by the previous theorem. And we know from this previous argument that x plus y quantity squared is less than or equal to this thing. And so that means this guy, the square root of that, must be less than or equal to this thing. Right, like so. And of course, the square root of this thing squared is just the thing. Right, that's the previous theorem. And so this is the triangle equality. That's exactly triangle inequality. That's exactly what we were after. Okay. All right. And closely aligned with the triangle inequality, we have the following. I would think of this as a corollary, but I'll write theorem here. So as a corollary for all x and y and r, we would have the absolute value of x minus y is less than or equal to x minus z absolute value plus z minus y absolute value. Okay. And secondarily, we could say that the absolute value of x minus the absolute value of y. Okay, so here you're taking the absolute value of two numbers and finding the difference between those, and then taking the absolute value of the difference. That's going to be less than or equal to the absolute value of x minus y. Okay, let's prove part A of this one just to see how quickly we can get to this just using the triangle inequality. So it's obvious that if we let's let x, y, and z be in R. Then if we start with the absolute value of x minus y, we know that that's equal to the absolute value of x minus z plus z minus y, right? That's just algebra, right? You can just do the algebra there and see that x minus y is the same as x minus z plus z minus y. Right, and then according to the triangle inequality, this piece here is less than or equal to the absolute value of the two pieces of the sum, right? So x minus z plus z minus y, right? This is just the triangle inequality. No problem, right? But that's the whole theorem, right? So you've got the difference is less than this thing. Okay, and so these are two that we'll use regularly. The triangle inequality we'll use all the time. These two will come up as well quite a bit. Right, and so all of this is important because we need to be able to reason about distances. Right, we need to be able to think about distances. And this kind of brings up the next idea, and that is that geometrically, we think of the absolute value of x as being the distance, from x to the origin. Right, so absolute value of x is really, we can think of it as the distance between x and the origin. So we can think of it like this. Now we have, sort of more generally, we can think of the absolute value as being kind of equivalent to the Euclidean distance. Right, the Euclidean distance. And we define that as, well, we'll use the notation dxy, but what we mean there is really just the absolute value of x minus y. Okay. Right, so for example, the Euclidean distance between the point -1 and 3 is just -1 minus 3, absolute value of that. And so it's just the absolute value of -4, so it's 4 units between these 2 points on the x-axis. And you can really kind of think of the Euclidean distance as being a function on r cross r. So dxy is a function on r cross r. Right, and it satisfies a couple of things. First of all, the distance is always a positive number, or 0. It's always non-negative. Secondly, if the distance is 0, then, well, that means x and y are the same value. So that means x equals y. Right, so whenever the distance is 0, that implies a very specific thing about the two arguments, the function. And thirdly, of course, dxy is definitely going to be equal to dyx, right? So, the distance between x and y is the same as the distance between y and x, of course. And finally, another feature of the distance function is that the distance between x and y is always going to be less than or equal to the distance between x and z plus the distance between z and y. Okay, and that's basically the previous statement, right? That's this thing right here, essentially. Okay, it's the same idea. Okay, and so we'll use this Euclidean distance concept a lot as we work through limit theorems, and it'll just be part of the machinery that we're using on a daily basis in analysis, really, I would say. Okay, so now I want to get, having talked through, kind of reviewed some of the principles of the absolute value and Euclidean distance, and laid out a little bit of the context for how we want to think about those things in analysis. I now want to turn to this idea of the neighborhood of a point. The neighborhood of a point, right? So this is not as convoluted of an idea as it maybe sounds on the surface. Really, what we're talking, so a lot of what we'll be talking about in analysis is going to require us to think about the idea of being, quote unquote, close to a point, right? So we'll need some terminology / notation to describe being close to a point, right? So if I say x is close to y, x is close to y, what do I mean by that? Well, the implication when I say that is that the distance between x and y is, quote unquote, small, whatever that means, right? So two numbers being close to one another implies that the distance between them is small, right? The Euclidean distance. And really the most convenient way to express this idea of close to is through the idea of an epsilon neighborhood. we'll consistently use the idea of an epsilon neighborhood, the epsilon neighborhood to describe when 2 points are close to one another. Okay, and so let's define an epsilon neighborhood. Let's define that quick. Okay, so we'll let P be a real number, and we'll let epsilon be greater than 0. Okay, so usually when we talk about epsilon, when we use this notation of this symbol epsilon to denote some real number, we typically mean epsilon is really small, right? So when we say let epsilon be greater than 0, we mean it's a small quantity, but positive, right? Off 0, small, but positive, right? So we'll let P be a real number, and we'll let epsilon be greater than 0. Then the set, and we denote it like this, n sub epsilon of P, right? So this is the name of a set. This is going to be equal to all of the real numbers x such that x minus P, the absolute value, is less than epsilon. This set is called an epsilon neighborhood of P, the point P. Okay, so we'll let P be a real number and epsilon some positive quantity, then the set n sub epsilon of P is all of the real numbers such that the distance between x and P is less than epsilon. Okay, and so this is kind of a way to define an epsilon neighborhood. Now, of course, another way to think about this, given the discussion we've just had regarding absolute values and distances and such, an epsilon neighborhood can also be thought of as all of the x in R such that P minus epsilon is less than x, which is less than P plus epsilon, right? And then, of course, if you're thinking about it in that sense, then the epsilon neighborhood of P is really just an open interval around P, where you've got P minus epsilon all the way up to P plus epsilon, open interval. Okay, so this would be an interval that's centered at P and has a radius of epsilon. Right, so you can think of it on a number line. You've got your P, and then up here and down here you've got P minus epsilon and P plus epsilon. And this whole thing here is just the epsilon neighborhood of P. Okay. All right. Okay, and so the idea here is that these epsilon neighborhoods, the way this will be used, and we'll see this in a moment how this is used, but just to kind of preface it a little bit, the way this will be used is we'll let epsilon vary, right? We'll let this positive quantity epsilon vary somewhat. I mean, it's usually what we'll say is that epsilon, let it be given, meaning they can be as small as you like. It can be arbitrarily small. Epsilon could be the value 0.00001. It could be 0.000000001. However small, arbitrarily small, right? And so what we mean is by an epsilon neighborhood is an arbitrarily small interval, open interval around P, right? So it could be as small as you like, right? As tiny as you like, right? And in most applications of the concept of an epsilon neighborhood, we really do mean a very tiny interval about P. Okay. All right. Okay, so what we want to do next is we want to jump into the idea of convergence of a sequence. And we're going to use this notion of an epsilon neighborhood as the sort of the central concept in the definition of the convergence of a sequence. So let's remember what we mean by a sequence. So by a sequence in R, we mean a function f from the natural numbers into the real numbers, right? And so for each natural number n in n, right, we would say p sub n is equal to whatever f of n happens to be. This would be the nth term of the sequence. Right, and we'll denote the sequence most often using something like this, p sub n in brackets, where n is equal to 1 up to infinity, or maybe just p sub n like this, with the implication being that the index set is the natural numbers. Most often that will be the case. Okay, so let's go ahead and define this. What do we mean by convergence? So here's what we say. We say that a sequence, and I'll denote it p sub n equals 1 to infinity, in R, a sequence in R is said to converge. It's said to converge if there exists some p in R, some real number p, such that, right, so there exists some real number p in R such that for all epsilon greater than 0, no matter how small epsilon happens to be, so for all epsilon greater than 0, there exists an n naught, natural number, such that p sub n is in the epsilon neighborhood of p for all n greater than or equal to n naught. Okay. All right, so let's pause for a second. There's more to the definition, but let's pause and think about what we've said so far. So we've got a sequence p sub n in R. We say that p of n converges if there exists another real number p such that for any epsilon greater than 0, I can find a natural number n naught such that the terms of the sequence are all inside the epsilon neighborhood of p whenever I get beyond that natural number n naught. Okay, that's the idea. And so let's think about what this means, kind of in a certain sense. So like, let's think about, here's p, okay, and let's just say I've got an epsilon neighborhood, p minus epsilon, and then p plus epsilon. So this is my epsilon neighborhood of p. Okay, and so my sequences starts maybe somewhere out here. I've got p1, and then I've got p2, and then I've got p3, and p4, and da da da. And so somewhere maybe up here I get to p10, and then I cross into the epsilon neighborhood p11, p12, da da da. And so you can see that the idea is that beyond p11, here n naught would be equal to 11. Beyond p11, all of the rest of the terms of the sequence, remember they're infinitely many, all of the rest of the terms stay inside this epsilon neighborhood, and indeed they actually get closer and closer as n increases to this value of p. Okay, that's the idea of convergence. And so remember this epsilon neighborhood, it says that for all epsilon greater than 0, that means I can shrink the epsilon neighborhood down as tight as I want around p, and all I have to do is find another n naught, right? So maybe to be inside of this epsilon neighborhood, n naught equals 100. And to be inside of this epsilon neighborhood, n naught equals 1,000, right? And I could just keep going. If I get a little closer, n naught equals 1,000,000, right? And so all the terms that come after the millionth term are all inside of this extremely tiny epsilon neighborhood right around p. Right? And so, as you can see, the idea is that the numbers get closer and closer to p. They never are equal to p. They just go right up to it. Okay. And so we'll frequently write this idea of a convergent sequence as, we'll think of it as a limit. So we say that p sub n converges to p. That's some of the terminology we'll use, converges to p, We'll also say that P is the limit of the sequence. Right, so this terminology you'll have heard from calculus. We'll also say just flat out that the limit as n goes to infinity of P sub n is equal to P, right? If Pn converges to P. You know, or we may, in shorthand notation, we may write things like P sub n goes to P, right? Meaning that the terms of the sequence converge to P. Okay? So that's the idea of a convergent sequence. Okay. And so, I mean, it was kind of illustrated in the way I was describing up here, but the key idea here, one of the key things to think about, is that this integer n naught, whatever n naught happens to be, depends on the selected value of epsilon, right? So n naught depends on the selected value of epsilon. Right, now in general, the way to think about it is that as epsilon gets closer, it gets smaller and smaller, then n naught has to get larger and larger, meaning you have to go further out in the sequence to be within the epsilon neighborhood, as if epsilon is really small. Right, if epsilon is you know, a nice wide interval, you might not have to go but 2 or 3 terms into the sequence. But if epsilon is infinitesimally small, then you're going to have to go a long ways out into the sequence before you're stuck in the epsilon neighborhood. Okay. All right. Let's do some examples. Now, I think the idea of a convergent sequence is very, so in my mind, it's very straightforward. It can be difficult to use this machinery to prove that certain sequences converge on. It takes a lot of practice. We'll do a few examples, but it really would be up to you as the student to dig into some analysis textbook and really like pull out example after example and just try a whole bunch of different examples. So let's consider the sequence. This is one we've seen before, 1 over n, where n, it goes from 1 up to infinity. Now this is obviously a convergent sequence. We know that 1 over n goes to 0 as n goes to infinity, right? We know that this sequence converges to 0. Let's try to prove it. Let's try to construct an argument using the idea of the definition of convergence to kind of to see that this is the case. Okay, so usually when you're writing a proof like this, you would say, let's let epsilon greater than 0 be given. Right, what that really means is that you as the prover of the theorem, or of the limit in this case, it's not on you to choose an epsilon. You have to construct an argument that will be responsive to any epsilon that's given to you, right? So we say let epsilon greater than 0 be given, meaning it could be as small as you like, arbitrarily small, and it won't, and the argument will hold up no matter how small epsilon happens to be. Okay, so we'll let epsilon greater than 0 be given. Then we know that this converges, so there exists some n naught natural number such that beyond the terms of the sequence, all of the terms of the sequence beyond n naught are going to fit within. We want to construct an argument such that all of the terms beyond n naught in the sequence will fit within an epsilon neighborhood. The way we usually do that is we use the Archimedean property, right? So we'll say there exists an n naught in n such that n naught times epsilon is greater than 1. Right? This is a good place to start for an argument like this. Okay, and so clearly, if n naught, we know that this is the Archimedean property, right? This has got to be greater than 0, right? And then this is your x and your y. X greater than 0, this is your y, and this is your n. And there's going to always exist some natural number n such that this is true. And of course, the implication here is that n naught is greater than 1 over epsilon. Okay, so we just need to, whatever epsilon happens to be, we just need to choose a natural number that's larger than 1 over epsilon. We'll do some specific examples in a moment with some specific epsilons. But the idea then would be like, so you give me an epsilon greater than 0. I can say, well, I'll just use this to choose my n naught. And then if I do that, then 1 over n minus 0, right? This is the distance between the point P and the terms of the sequence. We know that that's equal to 1 over n, right? And of course, n is a natural number, so this is the absolute value of 1 over a natural number is 1 over the natural number, right? And we know then that this is going to be less than epsilon, right? Right? Because up here, we would say that epsilon would have to necessarily be greater than 1 over n naught. And obviously, if n is larger than n naught, then this gets even smaller, right? And so the inequality would hold. Okay, I think it's really instructive to see what happens when we have very specific examples of epsilon. So let's consider a specific example of epsilon. So consider epsilon equal to 0.0001. Okay, so then if I say n naught times epsilon is greater than 1, and I actually plug in a small value of epsilon, n naught times 0.0001 has to be greater than 1. Right? Well, then I can see clearly that n naught needs to be greater than 1 over 0.0001, which we know is, if you do that division, that's 10,000. Okay, so n naught, my n needs to be larger than 10,000. Any term beyond 10,000, the 10,000th term in the sequence, will naturally be inside of an epsilon neighborhood with epsilon equal to 0.0001. Okay, so let's let n naught equal 10,001. Okay, then 1 over, what's the distance between 1 over 10,001 and, in this case, p is 0. So what's the distance between this term of the sequence and 0? And we would say that it's equal to 1 over 10,001, which, of course, we know, if you do the division here, is less than 0.0001. And, of course, the next term in the sequence would be as well. So 1 over 10,002 would also be inside the epsilon neighborhood. And 1 over 10,003 would also be inside the epsilon neighborhood, and so on, right? And to infinity. Anytime I make the denominator larger, I'm always obviously going to stay less than 0.001, so long as I'm beyond 10,000. Okay. So clearly there is, no end to this relationship. If I select a smaller epsilon, but one, of course, still greater than 0, then I just pick a larger n naught. Right? Right, and remember, this is all around some point p, right? So here's, p minus 0.0001, here's p plus 0.0001. If I tighten up the interval, I just have to shrink down. If I tighten up the interval, I just have to increase n, right? If I tighten up the interval, the neighborhood gets smaller. I have to go further out in the sequence to be inside the epsilon neighborhood. The point is that no matter how small epsilon gets, I can always go out a certain distance on the sequence to find the first term that's inside the neighborhood, and then all of them beyond that will be in the neighborhood. Okay, very good. Hopefully that's clear. It's a tricky concept at first, though if you've taken calculus, you probably have some idea of this. What about things like the constant sequence? Does something like this break our definition? So let's let p be in the real numbers, and the sequence p sub n will define the sequence p sub n to be the constant sequence where p sub n is equal to p for all n. Right, so for all natural numbers. I mean, so this would be like the sequence 2, 2, 2, 2, 2, 2, 2, 2 to infinity, right? Something like that. Well, then in that case, the distance between p sub n and p is equal to 0 for all n and n. Right, so you could take n naught to just be 1. Right, the first term has distance 0 from the limit point p. Right, and so on. And of course all of them do. Right, so this one fits inside the definition. It's just in this case, it's like the trivial example where the n naught, the first term of the sequence is really the key n naught here. Right. Okay. It's the term that works for any epsilon, as small as epsilon can possibly get. This one works. Let's try another example, something more complicated. Let's consider this sequence, 2n plus 1 over 3n plus 2, where n is a natural number. Now we know that the limit as n goes to infinity, this is just a ratio of two polynomials. We know that that limit is equal to 2/3, right? Let's try to prove it using the idea of an epsilon neighborhood and using like an epsilon proof like this, epsilon neighborhood style proof. Now, usually when you're given an expression like this, you'll have to start by thinking through what the sequence looks like. Right, and specifically what you want to look at is if I take the nth term of the sequence and I subtract off the limit, right? The absolute value of that distance, what is that? What does it look like? Right, and so this one you could do some work to this, right, to kind of combine this together. Right, and when you do something like this, you get, this is 6n plus 3 minus 6n minus 4. Right, and the top you could see is all just -1. Right, and so you can make it just positive, because this is obviously positive, the denominator, n is a natural number. So 1 over 3 times 3n plus 2, right? That's what this kind of boils down to. And then, of course, we can kind of expand the denominator here, and we get that this is equal to 1 over 9n plus 2. Now, 1 over 9n plus 2 is certainly going to be less than 1 over 9n, right? So this is smaller because the denominator is just a little bit bigger, right? And so this is a nice simplified way to think about the distance between the term of the sequence. Remember, n is in the expression here, so that the nth term of the sequence minus the limit point is going to be this kind of a distance here. And so if you can start by taking the nth term of the sequence and the limit and kind of combining it and making it making it a little more easier to interpret, then it's much easier to reason about what n naught needs to be in order for the convergence to work, right? And so let's let epsilon greater than 0 be given, and we need to choose an n naught based on epsilon. We need to choose an n naught natural number based on epsilon. Right, so remember, epsilon greater than 0 is given. It's arbitrary. We need to build our choice of n naught on epsilon. Right, and so you can think of it like this. If you have n naught times epsilon is greater than 1, then we can use n naught times 9 times epsilon greater than 1. And we can see that n naught needs to be greater than 1 over 9 times epsilon. Okay, and then we can just kind of plug all of this in. So if I have 2n plus 1 over 3n plus 2 minus 2/3. I know that that is less than 1 over 9n. Okay, but instead of n, I want to plug in, because so my n now is beyond n naught, right? So anything beyond n naught, I can plug in this expression for, right? So this is equal to 1 over 9 divided by 9 epsilon, right? And that's 1 over epsilon, or sorry, 1 over epsilon. The 9's cancel out, and so that's just epsilon. And so the relationship holds, right? That the distance between the nth term and the point 2/3 is less than epsilon, so long as n is greater than or equal to n naught. Okay? So long as n is greater than or equal to n naught. Okay. So this is a very typical kind of example. This is something that would be very easy in a calculus class to state the limit of, but here's how you might prove it using the definition. What about a sequence that kind of oscillates? So we saw earlier in the course the sequence 1 minus -1 to the nth power. Okay, the sequence diverges in R, meaning it just doesn't converge, right? And we know that if you plug in 1, you get 0. If you plug in 2, you get if you plug in 1, you get 2. You plug in 2, you get 0. You plug in 3, you get 2. So this thing oscillates between 2 and 0, right, forever. Right, so I mean, you could say on the surface there's no way this converges, of course, right? I mean, it's clear. But how can we see that it doesn't converge using the definition? Well, think about p sub n minus p. Right, p sub n minus p is always going to be equal to 2, isn't it? The distance between any two consecutive items is always equal to 2. Okay, so if it's easy therefore for you to give me an epsilon that this doesn't work for. If you say epsilon equals 1/2, then there's not exist a natural number n naught such that p sub n is in this epsilon neighborhood of p, well, for any p. So there's not exist an n naught, there also does not exist a p, right? So this is something that obviously clearly falls outside of the definition. There is no convergence here, and clearly, therefore, it must diverge. What about this example? We've seen this one probably in calculus class. Limit as n goes to infinity of the square root of n plus 1, minus the square root of n. Now this actually converges to 0. Can we prove that this converges to 0? Well, let's again start by noting what the absolute value between the nth term and the limit is. So the square root of n plus 1 minus the square root of n minus 0, right? So this is the nth term, minus 0 is the limit. Well, that's just the square root of n plus 1 minus the square root of n. Okay, and then we can do this nice trick here where we multiply the top and the bottom by the same thing. So, well, first of all, notice that I can get rid of the square roots, right? Because this square root is larger than this square root, so this is always going to be positive. So I can just write this. Okay, and then I can multiply top and bottom, as I was just saying, by square root of n plus 1 plus the square root of n, right? If I do this, this is just an old algebra trick that we've been doing since day one, right? If you can multiply this by basically multiplying by 1, right? And when I do that, the top I get square root of n plus 1 squared. And then I get minus or plus square root of n times square root of n plus 1 minus square root of n times square root of n plus 1. So those go away, and then I get minus the square root of n squared up top. Now in the bottom I still have n plus 1 square root plus n. Right? And so the nice thing about this, doing it this way, is that this is just n plus 1 and this is just n. So n plus 1 minus n is just 1. Right? So this whole thing looks like this. Okay. And then we can kind of make some executive decisions here. We know, for example, that the square root of n plus 1 plus the square root of n, we know that that's a larger number than the square root of n plus the square root of n. And that means that ratio is going to be smaller than this ratio, ever so slightly. And as the n gets larger and larger, that difference becomes smaller, but it's always, this relationship always holds, right? And so that allows us to kind of simplify this to 1 over 2 times the square root of n. Okay, right? And so here's a nice simplified expression for this distance. Okay, and it depends on n, of course. However far out you are in the sequence, that distance will be reflected in this value. Okay, so let's let epsilon greater than 0 be given. Okay, let epsilon greater than 0 be given. And we have to consider what n naught should be set to. Right, we have to find a natural number such that whenever we're beyond that natural number, then we're inside the epsilon neighborhood of 0. Okay, so let's set 1 over 2 times the square root of n naught less than epsilon. Right, and this is going to imply that 1 over twice epsilon is less than the square root of n naught. And that's going to imply that 1 over 4 epsilon squared is less than n naught. So we'll set n naught accordingly. And we need to let n be greater than or equal to n naught, right? And then when that's the case, so when n is greater than or equal to n naught, we have this relationship that we just kind of did the math on. N plus 1 minus square root of n minus 0, so that's the sequence minus the limit, is equal to, we did all this math already, we know that that's equal to 1 over square root of n plus 1 plus the square root of n, and we know that that's less than 1 over twice the square root of n, right? And so at this point we can plug in, we say it's less than, but we can plug in our value for epsilon, and it will, everything will nicely work out here. So this is the square root of 1 over 4 epsilon squared, and the math can be a little weird here, right? But it all works out. So this would be 2 times the square root of 1 over square root of 4 epsilon squared. So of course you get 1 over 2 over twice epsilon, and that equals epsilon. Right, so the important thing here is that we can see that n plus 1 minus the square root of n minus 0 is less than epsilon whenever n is greater than or equal to n naught. Okay, and that's the idea of the sequence being inside the epsilon neighborhood whenever we're far enough out in the sequence, right? And this is obviously, epsilon is arbitrary, right? You give me an epsilon, I can give you an n naught, right? Whatever epsilon you give me, I use it to calculate n naught, right? You tell me epsilon, I plug it into this, and it tells me what n naught needs to be. And then I can take that n naught and I can plug it into this expression, and you'll see that you get something less than epsilon. Okay. All right. Very good. So that was that'll be the last example, I think, of the of that. I mean, obviously we'll do lots and lots of examples as we go forward, but that'll be the last example for the section. Let's talk about a concept that depends on convergence somewhat, and that's the idea of bounded. We say that a sequence P sub n is bounded. It's bounded if there exists a positive constant m. If there exists a positive constant m such that the absolute value of P sub n is less than or equal to m for all n natural numbers n. Right, so this is a straightforward idea, right? If this is my n axis here, and the value of my terms are on this axis, and I've got some constant m, then the terms may approach m, but they'll never cross m. Okay? And so that's the idea of a bounded sequence. And as I said, this idea of bounded and convergent, they frequently go hand in hand. The first theorem is that if P sub n converges, right, then its limit is unique. And every convergent sequence is bounded. Okay? Right, so there's kind of two parts to this theorem. The first one says that, look, if I've got a sequence and it converges, then it must converge to a unique number. I don't think that's hard to visualize. How could a sequence converge to two separate numbers? Beyond a certain point, my epsilon neighborhood would be small enough such that both numbers aren't in the epsilon neighborhood. And at that point, only one of them could be the limit, right? The other one couldn't possibly be a limit because the sequence can't go to 2 points at the same time, right? That one's kind of obvious. The fact that every convergent sequence is bounded, I think, is fairly straightforward as well, but let's prove that second part. Let's prove the second part of the theorem, that every convergent sequence every convergent sequence in R is bounded. Let's let P sub n be a convergent sequence in R. Okay, so P sub n is a convergent sequence in R. And let's say that P sub n goes to P. Right, P is some real number. Okay, let's just start by taking epsilon equal to 1. Okay, then there is going to exist some n naught, natural number, such that what? Well, such that P sub n minus P is less than epsilon, which is 1, for all n greater than or equal to n naught, right? Okay. All right. Well, if that's the case, if P sub n minus P is less than 1, well, then by the theorems we've kind of talked through earlier, we can see then that P sub n minus the absolute value of P sub n minus the absolute value of P is less than 1. And that's going to mean that the P sub n is going to be less than the absolute value of P plus 1, right? And so we can, using this fact that beyond this point we can't be larger than P sub n, beyond this point, so we can use this fact and the following to basically identify the bound. So we'll let m equal the max of the absolute value of p sub 1, the absolute value of p2, right? Remember, these are all potentially larger, right? And let's just keep going forward until we get to p sub n naught. Okay. And then what do we need? Well, just p plus 1. Right? So one of these has to be the maximum. Nothing could possibly be outside of this could be larger, right? We've listed all the terms up front, and these things always have to head towards p, right? So beyond n naught, we're within an epsilon, we're within 1 of p. We know that for sure, right? That's by this piece here. Right? And so p sub n is bounded by m. And the fact that it converges means that it's bounded. Okay? All right, very good. Okay, I think we will end the lecture there. And when we get together next time, we'll continue on with these themes, these ideas, and we'll specifically jump into the limit theorems, and we'll start talking about limit theorems and how to prove them rigorously, similar way to what we've been discussing with sequences. So until then, take care.